Very bad.
Hi, everyone. As the chair of Yale's Department of Astronomy, it is my great pleasure to welcome you all to the 2025 Gruber Prize in Cosmology Awards ceremony. We are honored to host the Gruber Foundation here at Yale, and especially delighted to welcome Patricia Gruber, whose vision, together with Peter Gruber, created this extraordinary legacy. The Gruber Prizes celebrate fundamental discoveries, breakthroughs that transform entire fields and deepen our collective understanding of the world and the cosmos. It is a privilege for us at Yale to serve as the home of this remarkable tradition. Today, we gather to celebrate two exceptional scientists, Max Pettini and Ryan Cooke, the recipients of this year's Gruber Prize in Cosmology. Their pioneering work has opened new windows into the early universe, reshaping our grasp of its composition and its origins. So on behalf of the astronomy and physics departments and the university, I extend the warmest welcome to our distinguished laureates, to Patricia Gruber, and to all of you joining us for this celebration. Thank you for coming.
Welcome to the presentation of the 26th Annual Gruber Cosmology Prize, honoring a leading cosmologist, astronomer, astrophysicist, or scientific philosopher for theoretical, analytical, or conceptual discoveries leading to fundamental advances in our understanding of the universe. On behalf of all of us at the Foundation, we are pleased to be here at Yale, where the Foundation is housed, as Priya mentioned, to present this prize at the 6th Gruber Cosmology Conference. And we thank Priya for her warm welcome. The Cosmology Prize is presented annually in conjunction with the International Astronomical Union, whose support and partnership has guided our efforts from the earliest years. It is my pleasure to introduce Deborah Elmgreen, immediate past president of the IAU, who will say just a few words about our fruitful collaboration.
Thank you, Sarah. The IAU is pleased to have collaborated on the Gruber Cosmology Prize since the prize's inception. The IAU has an advisory role in the constitution of the Selection Advisory Board. As part of our collaboration, we are fortunate to receive an annual grant of $75,000 to be awarded to postdoctoral fellows from around the world so they may pursue education and research at a center of excellence in their fields. To underscore the scope of this prize, the fellowship has been awarded to 40 young scientists so far from Algeria, Chile, Poland, Taiwan, India, Spain, Italy, Israel, Greece, Belgium, the Netherlands, Russia, Mexico, the UK, Colombia, Egypt, Ecuador, Madagascar, China, Brazil, Iran, Australia, Peru, France, Ukraine, Romania, and the United States. Half of the winners have been women. The 2025 fellows are Jalen John Bartlett from the UK, Sambatriana Hagarishe Asha Rajanson from Madagascar, and Akshara Viswanathan from India. Thank you.
And I send my congratulations to the 2025 Gruber IAU Fellows, and thank you, Deborah. We wish they were here with us today. They may be watching the live stream that we started with the ceremony. So the Gruber International Prize Program, established in 2000, recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. While we are here to honor the achievements of Ryan Cooke and Max Pettini, let me mention that the 2025 Genetics Prize was presented on August 23rd to Rotem Sorek, and that the Neuroscience Prize will be presented on November 16th to Edward Chang. Please also note that nominations to the 2026 Gruber Prizes are open until December 15th of this year, and that we encourage nominations that reflect the breadth of the field and the diversity of those working within it. Before we return to cosmology, I would also like to acknowledge our co-founders, Peter and Patricia Gruber, whose combined vision and leadership established this international prize program, and whose care in doing so gave it the legs to stand on its own. Peter has passed, but Pat is still the heart of the program and a lifetime member of the board of directors, and of course is here with us today. Returning to cosmology, we are proud of our illustrious laureate roster, and we're pleased to be adding to it today. The 2025 prize recipients were selected by a distinguished selection advisory board. We deeply appreciate the knowledge, commitment, and enthusiasm that the advisors bring to the judging process. And I will now invite the chair of the selection advisory board, Louis Ho, to present the official citation and introduce the scientific accomplishments of our recipients.
Okay, the big moment has arrived. I've never hosted the Oscars, but this is like a mini Oscars. So first, the official citation. It reads, the Gruber Foundation is pleased to present the 2025 Gruber Cosmology Prize to Ryan Cooke and Max Pettini for bringing the light element abundances in Big Bang nucleosynthesis into the realm of precision cosmology. By finding and selecting the most pristine quasar absorption line systems in the high redshift universe, unaltered by star formation, and by leveraging the capabilities of some of the largest ground-based telescopes, Cooke and Pettini obtained a 1% measurement of the primordial deuterium to hydrogen ratio. This meticulous work has made possible a Big Bang nucleosynthesis-based determination of the baryon density of the universe with precision comparable to that of a cosmic microwave background determination, enabling important consistency tests of early time physics between t equals 1 second and t equals 400,000 years. That actually gives me chills every time I read it. The fact that science can do this, and this is not science fiction. So just a few words of my own reflection on this, even though I don't work on cosmology. We all can agree that the hot Big Bang model for the origin of the universe has been one of the true testaments of human knowledge, one of the most successful theories in modern science, in no small part because several of its foundational premises can be tested through rigorous observations. Now, one of the key parameters of the model is the so-called baryon density, the relative density of baryons to photons. Okay, it's a very small number, it's 6 times 10 to the minus 10. Now, there are two main ways that we can experimentally try to crack this problem. The first is through measurements of acoustic oscillations as traced by the cosmic microwave background. The second approach, which is being honored today, is to measure the primordial abundances of the light elements, namely hydrogen, helium-4, and deuterium. Now, in contrast to the CMB, which of course traces the surface of last scattering, the universe was 400,000 years old, the fusion of the nuclei occurred much earlier, merely a few seconds, up to about 20 minutes or so after the Big Bang. This time, the temperature of the universe was cool enough for deuterium to survive, but hot and dense enough for fusion reactions to occur at a significant rate. Now, most of these fusion reactions during BBN terminated in production of helium-4. But not all reactions are complete. The incomplete reactions lead to small trace amounts of leftover deuterium. The key point is that the amount of deuterium decreases with increasing baryon density. The higher the baryon density, the more reactions there'll be, of course, and more efficiently, deuterium will be eventually transformed into helium-4. The primordial deuterium to hydrogen ratio is especially critical because deuterium is easily destroyed in stars, and it's not significantly produced by later astrophysical processes. Therefore, the amount of primordial deuterium that survives to be observed today is exquisitely sensitive to the density of baryons at early times. Okay, so that's the key power of this technique. So this all sounds fine, right? But how to realize it is truly non-trivial and is a real tour de force. The key experiment, as all of you should know, is to measure the deuterium lines there in the ultraviolet. You all know Lyman alpha at 1216 angstroms. Well, the Lyman alpha line of deuterium is just a wee bit bluer, 0.3 angstroms, okay? So it's badly blended with the hydrogen series. So the key is how to separate them. So the experiment is to seek really distant quasars that are absorbed by foreground intergalactic gas, but it has to be very, very pristine, very low metallicity, right, in order for this to work. So this requires first finding these things. They're really rare. So that's already an arduous task that you have to do in advance. Then you need to observe them with the biggest glass available on the ground. So that will be Keck on Hawaii, 10 meters, the VLT at ESO, because they're very far away, okay? And then you need a in-shell spectrograph, tens of thousands resolution, because these are tiny separation that you need to resolve, right? So you need really high signal noise ratio, really high spectral resolution. It's really painstaking work. I consider this to be truly an extraordinarily elegant experiment because these days, you know, cosmology is done by huge teams, right? You know, huge experiments, extraordinarily expensive on the ground and in space. It is really rare, I think almost poetic, that such a fundamental observational constraint on cosmology can still be done through the methods of classical astronomy. The younger people here may not know what I'm talking about, but dinosaurs like me, who used to travel to mountaintops, okay, you know, take a finding chart, you know, nervously drive up there, prepare in the afternoon, pray that the weather holds up. Sometimes it doesn't. Maybe everything is perfect, but the instrument doesn't cooperate. These are the vicissitudes of being a classical observational astronomer. In this particular case, this work was primarily done by two individuals with the help of some friends, of course, using instruments that by today's standards could be considered modest in size and complexity. So I think this is extraordinarily beautiful. Kudos to Ryan Cooke and Max Pettini, whom I now formally invite to the stage to accept your prize. Great.
Guess you win some, you lose some. Well, I just want to say a few quick words of appreciation. First of all, I want to thank you all for being here today to celebrate with us. It means a lot to us to have you here. There's one thing that I've really learned in this process and that I've accepted, and that is that I'll be in denial for the foreseeable future. But I'm nevertheless extremely grateful to the Gruber Foundation for their support of science and of cosmology, and in particular, the support they've given to young scientists as well. And I think this is truly tremendous. I also want to thank the committee that considered the work that Max and I were doing to be worthy of such an award. It's just science that Max and I love doing. And so it's a truly honor. And so thank you very much as well for considering this work in the same way. My family couldn't be here today, so I want to dedicate this to those that couldn't be here. My wife and two kids, they're the center of my universe, and I'm very lucky to have them in my life. I also want to thank my parents for all the support for many, many years. And finally, I also want to thank Max. And there's a good reason. It's because very few people have the privilege of having worked with Max. And so what I will take with me for the rest of my academic career is the scientific knowledge and rigor that you've given to me. And so it's a real pleasure to work with you over these years. And I hope it continues.
Thank you very much, Louis, for your kind words, and Ryan, of course. The pleasure was all mine. I feel truly humbled to be receiving this prize today and to see our names alongside those of the most influential cosmologists of the last 25 years, which is often described as a golden era of cosmology. I can only repeat some of the things that Ryan said in thanking the Peter and Patricia Gruber Foundation and applauding their generous, continuing support to science through the international prize programs and Young Scientist Awards. These recognitions and encouragements are all the more important during these troubled times when science finds itself incomprehensibly under attack. I'm also grateful, of course, to the members of the Cosmology Selection Advisory Board, whose job is made difficult as well as pleasant by the fast pace of advance of discoveries about our universe. I'm grateful also to Slava Mukhanov, who proposed us for the award, and of course to our hosts here at Yale University for organizing such an interesting and fun event that we've witnessed today. And finally, I should like to acknowledge the Institute of Astronomy of the University of Cambridge, where both Ryan and I worked. They provided a stimulating intellectual environment from which both of us have benefited over the years. Thank you very much. Let's just get a talk up. See if it works. You should do. And here we are. No, you're good. Over here. Very good. So what Ryan and I are going to do in our joint talk is to explain why and how we've been able to measure the abundance of deuterium to 1% and the implication of our measurements, although you've heard all afternoon already much of the story. My half of the talk will include some of the background to our work, while Ryan will take us right up to date with the latest developments. So what excites me about Big Bang nucleosynthesis is the fact that you can actually probe observationally this early epoch of the universe. Sorry, this is not dated. Okay. We need some help here. Okay. The slides are not updating. It says it's paused. Yeah, there. So I was saying what excites me about nucleosynthesis is the fact that observationally we can reach to this very early stage in the history of the universe, much before the time when the universe cleared itself after the cosmic microwave background was emitted. We can reach these first few minutes with our own observations now from the ground, from Earth. The seeds of this idea go back to the late 1940s, when George Gamow, his PhD student Ralph Alpher, and Robert Herman first realized that if there was an initial dense hot region of the universe, neutrons and protons could combine to synthesize the elements of the periodic table. The ideas laid more or less dormant for some 20 years, until in 1964, the cosmic microwave background was discovered. And soon after that, papers were published, and they picked up the idea and did the first calculations on the nuclear reaction involved quantitatively. This was the first one I knew about by Jim here. You can see primordial imperium abundance and the primordial fireball. This was 1966. And the following year, Robert Wagner continued the study, produced first some of the first calculations. As he says here, a record of the fireball phase of the universe may be containing abundances of the sign some light nuclei. And if you look back at this paper from 1967, the figure 1, which shows the nuclear reactions involved, is not very different from this slide here. The only difference is that in 1967, in papers, you couldn't produce figures in color. But it's all here. It's all in this. This is what primordial nucleosynthesis is. You combine protons and neutrons, and then eventually all the neutrons end up in helium-4 with small traces left in deuterium and helium-3 and lithium. And as we have heard already several times today, essentially the small amounts that are left in deuterium, helium-3 and lithium, look at the scale on the y-axis, is 10 to the minus 4, 10 to the minus 5, 10 to the minus 9, 10 to the minus 10. Tiny amounts depend on the ratio of baryons, the matter, ordinary matter, to photons. This parameter eta is on the x-axis. We know the density of photons very accurately from the black body spectrum of the CMB. So essentially, on the x-axis, we have matter density. On the y-axis, we have the ratio of these elements, these primordial element ratios. And apologies. And it was Michael Turner at Chicago and much missed Dave Schramm who pointed out that deuterium is probably the most sensitive of these light element abundances to the density of baryons. It's the baryometer of choice, a phrase coined by David Schramm. And you notice, like you heard from Louis' introduction, that the higher the matter density in the universe, the less amount of deuterium is left over at the end of Big Bang nucleosynthesis. So it's inverse proportionality. But the deuterium curve, that blue curve in this plot, is very steep, and that it means that you can measure, if you measure the deuterium abundance to sufficient precision, you can get a handle on the matter density. So measure deuterium or any of the other elements here with sufficient precision, and you can literally weigh the whole universe, at least in ordinary matter, not in dark matter or in dark energy, but in the baryons that make up the world as we know it. To my knowledge, the first detection of deuterium was in the interstellar medium of the Milky Way, close to the Sun, in the spectrum of the star Beta Centauri. It was one of the first results from the Copernicus satellite in the early 1970s. The Copernicus satellites, for those of you too young to remember it, opened the doors to ultraviolet astronomy completely. It was the first high-resolution UV spectrograph we've flown into space. And in some ways, it's not been better yet. So this paper was published in the first batch of papers in 1973 by Rogerson and Don York. I couldn't find an image of John Rogerson. Don York was then at Princeton, he's now in Chicago. Measured the detected deuterium, and here's the detection. They were smart enough to recognize that this. Try another one.
Try your mouse, because then it will show up on both screens.
This is better. That this little blip here in the blue wing of this broad feature, which is the hydrogen lemon gamma seen in Beta Centauri, this blue dip here, the additional absorption, is the isotope shift, is deuterium in the local ISM. So that was the first measurement of it. And so to explain that a little bit better, as most of you must know by now, there are various energy levels to hydrogen on the left here, and the absorption of a photon from the ground state to the first excited level will produce a hydrogen Lyman alpha line, to the second excited level, Lyman beta, so all the way up to the Lyman continuum. And exactly the same is the case for deuterium, of course, because deuterium is, after all, hydrogen. It's just an isotope. The only difference is that it's got that neutron in the nucleus. And as a result, all of these energy levels for deuterium are shifted up to slightly higher levels. And that means that all of those absorptions then require a little bit more energy, or the absorption lines are slightly shorter wavelengths. And the shift is only 82 kilometers per second in velocity terms. It's a small shift. Nevertheless, it's the largest isotope shift of any other element. If you look at carbon, oxygen, and so on, those isotope shifts are very much smaller and much more difficult to detect. Okay. So Don York and Rogerson could only measure an upper limit to the primordial abundance of deuterium from their measurement, from their very first measurement. And the reason is that whenever gas is turned into stars, two things happen. Stars burn deuterium, and so there's much less left today than was present at the beginning of the universe, but also the stars make all the elements of the periodic table, which astronomers confusingly call metals, and physicists hate us for doing that. But we just use it as a shorthand for anything that is made in stars, as opposed to primordial nucleosynthesis. So we have these two effects. Whenever you process gas into stars, through star formation, you make some carbon, nitrogen, oxygen, but you destroy deuterium. And of course, in the Milky Way today, the ISM of the Milky Way, 13 solar giga years after the Milky Way was formed, means many generations of stars, and therefore there's only a fraction of the deuterium left from what was there at the beginning. And what we want to know is how much was there at the beginning with great precision. So how do we measure the primordial abundance of deuterium? And the answer is via absorption lines in near pristine clouds in the distant universe. And Gwen, in the first talk this afternoon, has already showed you the technique of absorption line spectroscopy. It's quite straightforward. Quasars are the most luminous objects, some of the most luminous objects in the universe. We can see them to large distances. Their spectra, on their way to Earth, carry with them the imprint of all the material that's between the quasar and us in the form of various absorption lines. And you see here various classifications in this slide of different absorption lines. But the point to remember is that almost all of the lines that are here are shorter wavelengths. And this is laminar emission in the quasar. All of these lines are laminar flow lines, lines in the laminar series of hydrogen. We'll come back to that in a second. Okay. So also the next one to draw attention to this real visionary paper by Thomas Adams, written in 1976. Again, I couldn't find a picture of Thomas Adams, but notice this is the third time I'm mentioning Chicago in this talk already. And he pointed out that it's shown suitable clouds in deuterium and alpha lines should be detectable in quasar absorbers, and observers should be alert for the deuterium laminar alpha line, since its detection would have important cosmological implications. So Adams said this in 1976, well ahead of the time when we could carry this idea forward. We had to wait 20 years until the advent of the Keck telescopes to have the instrumentation capable of carrying out this observation. And here the twin Keck telescopes from Mauna Kea, and this is the first paper that used the Keck to report a detection of deuterium in a high redshift in a distant low metallicity cloud by David Tytler and his collaborators. Here's their data, and you'll see that in the first, starting from the top, in the first two lines in the Lyman series, Lyman alpha and Lyman beta, he was able to detect that blip on the left-hand side, that on the short wave side, which is deuterium. So this is 20 years after the Adams paper, and this is the result from this initial observations by David Tytler. He could measure an abundance of deuterium to hydrogen of 2.3 times 10 to the -5. Now free for the problems of astration of this consumption of deuterium to stars, but look at the error, a 25% error in this measurement. Again, this was exploratory data ahead of its time, but not quite good enough 30, 40 years later. 30 or so years later, when we want this number with much higher precision. So let's return to this quasar spectrum, and here comes, if you like, our own contribution to this long quest for the primordial abundance of deuterium. I showed you lots of different absorption lines. You can see lots of different absorption lines in the spectrum. They're different. Some of them are weak, some of them are strong. Essentially, what you're seeing is a distribution of mass in the absorbers, in the clouds in front of the quasar. And this distribution of mass, or column densities, if you like, spans 10 orders of magnitude. So there are clouds with only 10 to the 12 on the left-hand side of this plot, atoms to the per centimeter, and some clouds with 10 orders of magnitude more. The ones with 10 to the 20 or plus atoms hydrogen per square centimeter give you these characteristic profiles, which we call damp laminar alpha systems. There you see at the top of this image, and you can think of them as early galaxies selected by neutral hydrogen absorption. And this is a good point to remember the father of the subject, Art Wolf, who really was key in drawing people's attention to the DLAs, to the damp laminar alpha systems, and all the things you could do with them. You could study early star formation. You can study the conditions, as we heard from Gwen, in clouds of different redshifts in the universe, and you can measure it. You could use them to measure deuterium, which is what we concentrated on. So, if we look now, what I was going to say here is that when Art's first paper had maybe 20 or so these DLAs, there are tens of thousands of them known now, thanks to large-scale surveys in the sky, like the Sloan Digital Sky Survey, which was the brainchild of Jim Gunn, who you may remember was one of the previous recipients of the Gruber Prize. If you look at the metal lines that Gwen was mentioning this morning, if you measure the composition of this gas, you find some interesting things. So the first thing you find, and I have to explain this plot for the non-experts. So this is a distribution of metallicities, or if you like, the oxygen abundance in the system. And a point here would have the same oxygen abundance as the sun or the Milky Way today. On the x-axis, you have a log scale. So this is 1/10 of solar, 1/100th of solar, and 1/1000th of solar. Now, most of these damper alpha systems are less enriched than the Milky Way today. We've seen them at earlier times in the history of the universe, and they're probably lower mass systems anyway. But there's a tail at both ends, and what we're really interested in is this low metallicity end, with metallicities of down to 1/1000th of the Milky Way today. So these are the ones that we're after, because at such low levels of chemical enrichment, they're the ones who are likely to have the primordial abundance of deuterium with confidence. There's been no destruction of deuterium through stellar nucleosynthesis. Remember, whenever gases turn into stars, deuterium is burnt and metals are made. So if you find a system with very few metals made, it's likely that the deuterium, very little deuterium, if any, has been burnt in the process. So I would argue, we've shown this now, that these very metal poor DLAs that tail at the low metallicities of the damper alpha system population are the choice environments, astrophysical environments for measuring the primordial abundance of deuterium. One reason is the low metallicities imply negligible destruction of deuterium. The second reason is that there is actually a relationship between the amount of metals made in these systems and how narrow or wide their absorption lines are. So the narrow, this most metal poor DLAs, here's an example. The fit to the hydrogen line at the top of the figure gives you an accurate measure of the column density. And you see how, you can see here how weak these absorption lines from carbon, oxygen, aluminium, silicon, sulfur, all these elements that we see in the spectrum, these lines are weak. The metallicity is only 1/200th of solar in the system, but look how narrow they are. If you look at the velocity scale of these plots, the width of these lines is a few kilometers per second. These are low mass systems where the temperature is low enough and the turbulence is produced by gravitation is so low that those lines are very, very narrow. And that, of course, is ideal for resolving this 82 kilometers per second isotope shift between deuterium and hydrogen. So that's the second advantage. And of course, the third advantage is that with such high hydrogen column densities, they give us detectable deuterium lines in many transitions of the Lyman series. So you may remember I showed you the first spectrum obtained by David Tytler. There are only 2 lines in the Lyman series that showed you the deuterium shift, the deuterium absorption. That was a low column density system. Now look at this system here. Again, a good fit to the hydrogen Lyman alpha from gives us an accurate measure of the hydrogen column density. This system is only nearly 1/1000th of solar in iron. But now look at this composite of all the lines in the Lyman series. We see the deuterium component of the Lyman series all the way through Lyman alpha, beta, gamma, delta, all the way to Lyman 17 or Lyman 18. We have almost 18 independent measures in the spectrum of the deuterium absorption.
I'm having trouble seeing the last 3.
Well, here's the component,
Yes.
and I guess
Well, that's
we
a
lose it by
little
about
much. That's too
17.
much.
Yeah, the way to understand these spectra is that, of course, as you go higher and higher up the Lyman series, the transitions become less and less likely. The transition probability gets lower, which is something that helps us to assess the column density of deuterium, because the lines line on different parts of the curve of growth. We can build up the curve of growth very accurately with this amount of data. And also, the Lyman series lines get closer and closer and closer together. And so at some point, you stop. Yeah. So if I made it sound simple so far, let me tell you, it isn't simple. It's actually a very delicate experiment because everything has to be just right. The redshift of the quasar has to be right. The brightness of the quasar has to be right. And then the redshift of the down-plumb alpha system has to be right. Its metallicity has to be low. And we need lots of telescope time to collect data of sufficiently high signal-to-noise ratio to make this experiment. And the fact that it's a delicate measurement explains why, after about 10 years of effort, we have a precision sample of 8 such measurements. That's it. Despite the fact that tens of thousands of DLAs are known, there's 8 so far at the right redshift, the right magnitude, the right properties for us to make this measurement. And each of these points here required at least one, if not more than one night on either the Keck or VLT telescopes. So if we take a weighted mean of these measurements, we get this value of the primordial abundance of deuterium, which is precise to just about 1%. 2 things to note before I pass on to Ryan. One is that these 8 measurements all agree with each other within their estimated errors. This was not always the case at the beginning of the subject. There were often discordant measurements reported. It's partly the choice of the sight lines used, and partly the fact that Ryan in particular developed a very robust and statistically robust method to measure this number from the spectra. So, and it's been done consistently for all of them in the same way. And incidentally, we don't look at the result until the fit. We reckon the fit is as good as it's going to be. Then we unblind the answer. Okay. So that's the first point. They all agree with each other with the errors, and we're confident that it gives us confidence that this number is the there's written here at the bottom is the primordial abundance of deuterium. And the other point is this black line through the points is the results, shows you a galactic chemical evolution model that calculates at these metallicities. Again, you see these DLAs and metallicities of less than 1/30th of solar down to almost 1,000th of solar if you look at the x-axis. And that black line, it tells you the calculation of how much deuterium has been destroyed. And essentially that's next to nothing for most of the 8 points here. So abstraction is not an issue. And this is the right time for me to stop and pass over to Brian.
Great. Thank you very much, Max. Max has done an excellent job describing how we went about obtaining this extremely precise measurement of the primordial deuterium abundance. And this is just half of that story. And so in our joint talk, I'm now going to talk about the other half of the story, and that's how we take this measurement and we do cosmology with it. Now, it's just a small thing we're going to go for the next 20 minutes, because Max has done about a decade of work in the space of 20 minutes, in the space of, so I'm now going to do the exact same. And in my 20 minutes, I'm going to tell you how we measured the weight of the universe, just a small thing. So just in case you all feel very inspired after today's conference, and you think, you know, I'm going to go home and I'm going to do a calculation of BBN myself. Okay, that's your choice if you choose to do that, but it would be irresponsible of me if I did not give you the ingredients that you need to know to perform your calculation. So there's really just 2 things you need to know. The first thing you need to know is the baryon density. These are the things that are in the early universe that are joining together to make the deuteron nuclides. You also need to know the expansion rate of the universe, and that's the thing that's driving these baryons away from each other and changing the temperature of the universe. So those are the two key parameters that you'll need. And if you want to assume for the standard model, which is a very good assumption at the moment, then you need to make three key assumptions. The first is the probabilities that these reactions will take place, the nuclear reaction cross-sections. They're measured in the laboratories today, and they're also calculated from first principles. And we have to assume that the ones that we calculate and measure today are the same now as they were a few minutes after the Big Bang. And that's not necessarily a guarantee, but that's one of our assumptions. We also have to assume that general relativity is the correct description of the universe. This, of course, means we want to be able to relate the contents of the universe and how that causes the expansion. And finally, the standard model of particle physics has three families of neutrino species. And so I'll revisit this a little bit later, and we might relax this assumption. Okay, so I mentioned that one of the key things we need are these reaction rates. And so I wanted to take a quick pause to thank the nuclear physics community, because they've done a tremendous amount of work in building these reaction rate networks that are needed for us to do cosmology moments after the Big Bang. I'm showing in particular some work here by the LUNA collaboration, Laboratory for Underground Nuclear Astrophysics. And so when Max and I were first measuring these the primordial deuterium abundance with such precision, we had recognized that this reaction rate called dp gamma, it's where deuterium is destroyed by a proton and releases a photon. We realized that this was kind of the limitation in our ability to interpret cosmology. And so Max was at the Great Barrier Reef and stumbled into someone who was at LUNA and mentioned that this was really important to us. And 5 years ago, the LUNA collaboration reported this key measurement, which has driven down the nuclear reaction rate uncertainties and has enabled this precision cosmology as well. So this is a general thank you to the nuclear physics community for their work in this field. Okay, so you now have everything you need to build this calculation. Here's one that I prepared a little earlier. We're going to start about 1 second after the Big Bang or thereabouts on the left side of this plot. And this is when the universe was basically filled, the baryon content of the universe was basically just protons and neutrons and nothing else. Okay, and these protons and neutrons were roughly in equilibrium. Some of them were sticking together, but then the photons of the background radiation were tearing them apart again. But 1 in a trillion of these protons and neutrons stuck together to form deuterons, which is the deuterium nucleus. Now, as the universe continued to expand, it got cooler. It also became less dense. And so it became more favorable for these protons and neutrons to stick together more often than they were broken apart. As the universe continued to expand to about 3 minutes after the Big Bang, or thereabouts, almost all of the neutrons available in the universe got sucked up into helium-4. And so the abundance you see here, about halfway along the plot, at around a few minutes after the Big Bang, that set the amount of helium-4 that was made just moments after the Big Bang. The rest of the nuclides took a bit longer to freeze out their abundances. And so they probably finished around somewhere between 8 hours to 24 hours after the Big Bang. And so we need to run these calculations all the way to about 1 day after the Big Bang to get our final abundances that we expect given the inputs that we put into our calculation. This particular calculation was performed with links, which we saw earlier on today. So the focus of this is about deuterium. So let me focus here by giving a bit more information about how deuterium is sensitive to the baryon density of the universe, which allows us to weigh the universe in baryonic matter, stuff that you and I are all made. Okay, so first of all, we start with our calculation and we throw our baryons in. And what we're going to do is normalize this or register it relative to the density of photons. We call this parameter E to 10, or the baryon to photon ratio. It's just a amount of baryons you have relative to photons in some given volume. And so we change our calculation to have different baryon to photon ratios. As you can see here, the red has a low baryon to photon ratio, and the gold at the bottom has a high baryon to photon ratio. And this produces different amounts of deuterium relative to hydrogen. Now, we can also turn this argument around, and if we can measure the deuterium to hydrogen ratio in primitive environments, we could back out this eta 10 parameter, which tells us the baryon density of the universe. That is the simple experiment. Now, it's not just deuterium that's sensitive to this parameter eta 10, the baryon density. All of the nuclides that were created moments after the Big Bang are sensitive. But as Max mentioned, it's deuterium that's the baryometer of choice. It's the one that's the most sensitive to the baryon density. And so what you see here in this plot is the number abundance ratio on the y-axis. And so you see the relative abundance of each of these nuclides relative to another nuclide that was made during this first few moments as a function of this parameter eta 10. Okay, so I'm going to, for a moment, mention again that this eta parameter is sensitive to the baryon density of the universe. And we know that the baryon density can also be measured from the temperature fluctuations that are imprinted on the cosmic microwave background radiation, as seen here, recorded by the Planck satellite. And that's represented by this gray band that you can see on the left plot. Now let's for a moment zoom into this region where the gray band and the blue band intersect each other. So the deuterium theory curve is this blue line. So what we could in principle do is take this gray band, see where it intersects our blue band, which is the theory calculation, and track it across to our y-axis to estimate how much deuterium was made in the first day of the Big Bang. We can also turn this around and say, well, if we can confidently measure the primordial deuterium abundance, we can track this across horizontally, connect it to our blue theory curve, and get an independent measurement of the baryon density of the universe, and can compare that to the cosmic microwave background radiation. And if we do that, we end up with stunning agreement. Now, I want to mention a few things here. First of all, Max and I were doing these precision measurements prior to when the Planck CMB results came out, and prior to the Lunar collaboration reporting their results for DP Gamma. I also want to point out something I think is truly remarkable, which Lewis mentioned at the beginning of the ceremony today. And that is we have two completely independent probes of the baryon density. One is in the first day of the Big Bang, one is hundreds of thousands of years after the Big Bang. Not only that, but they're completely independent physics. Not only that, in order to get these two independent measurements, we needed to understand astrophysics. We needed to understand fluid dynamics. We needed to understand cosmology. We needed to build our cosmological model. We needed to understand particle physics and nuclear physics. And all of this relies on us building instrumentation, not only that we send to space to get these CMB measurements, but also the largest telescopes and the most exquisite spectrographs on the largest telescopes. We are pushed to the limit of our current instrumentation, and these two completely independent techniques agree to 1%. This is not just a remarkable agreement. This is a remarkable test of science that these experiments from multiple different fields of physics have all converged to this experiment of Big Bang nucleosynthesis and the CMB, and we get 1% agreement. And I think that's a testament to human knowledge of our universe. And that's what I'm most excited about. So for those of you who don't like contours, I'm showing this in a different way. If you're a numbers person, you can just read the numbers at the bottom of the slide. Another way is this plot that Max showed earlier in this talk, showing the 8 precision measurements of the primordial deuterium abundance. The red lines show you the weighted mean, and the gray shows you the CMB, and they overlap nearly perfectly, as do the numbers. Okay, so I'm now going to show an obligatory pie chart, which I think only ever appears in cosmology. So I think it is a really important chart that we understand, because this baryon density tells us that the universe in baryons, which is us, the table, the chairs, people, planets, stars, the ordinary matter of the universe is 5%. And we have two independent probes of that tell us 5%. We also know that we don't know most of what the universe is. We know that it's there, but we don't know what it is. And I think that's a really exciting time, because there are these cracks that we can already observe that makes us excited that around the corner we may just well detect some new physics that leads to a revolutionary discovery. And that's hugely exciting. I also wanted to point out part of this pie chart that you can't see on this plot, but it's extremely small, but it's extremely important. And I don't think I've ever seen it before written on this pie chart. And that is omega u. This is the genuine fraction of the universe. That is the atoms and molecules that you are in control of, that you decide. And I find it incredible that this tiny fraction of the universe, this omega u, is capable of understanding omega critical. I find that amazing. So this is omega u, it's omega me. Although I'm half expecting my 3 to bump up to a 4 after dinner tonight. But this is, I think, most exciting, that one of these omega u's will help one day to figure out the rest of the 95% of the universe. And I'm excited by that. Now, we've already understood that there are cracks in the standard model. We don't understand 95% of the universe. And there's also properties of neutrinos we don't understand, of particle physics. There's lots of exciting things, I think, for cosmology just around the corner. And I wanted to discuss now how we can use the primordial abundances to help gather an understanding of what might be around the corner. So this plot that you can see on the left of the slide is exactly what you've seen before for the rest of the talk, except for the rest of the talk, it was just the green curves. What you're seeing is the abundance of these nuclides that were made just after the Big Bang as a function of the baryon to photon ratio, same as before. But now we're changing the other parameter, which is the expansion rate of the universe. And if we change the expansion rate, it changes the relative abundances that are made. And that's shown by these other curves. Now, cosmologists use this parameter n effective, which is the effective number of neutrino species. It's just a way that we change the expansion rate of the universe, and that could be coming from a multitude of different things. But each of these different things leaves a fingerprint on the primordial chemistry of the universe. And so we can use these chemical abundances that we measure moments after the Big Bang to help understand and place limits on departures from the standard model. Some topical examples are dark radiation, sterile neutrinos, axions or axion-like particles, and these are kind of towards the best guesses that we currently have for what might be causing the dark matter in the universe. So I wanted to take a pause and talk about some other work that Max and I have been doing and look to the future of Big Bang nucleosynthesis. And I wanted to talk about a new measurement that we're currently looking into, which is very exciting. We're going to go from one side of the universe all the way to our backyard, or our galactic backyard. Those of you may recognize this as the Orion Nebula, and the arrow is pointing to one of the brightest stars in the Orion Nebula. You can almost see it with your eyes, 5th magnitude. And we decided to observe this star with one of our biggest telescopes for 30 minutes. And we used this instrument, CryoRes Plus, which is a refurbished instrument. And we went to measure an infrared absorption line from helium. And I should mention the helium absorption lines that you see in the bottom of this slide. These have been known about since the 1930s. So almost 100 years ago, we've known about these absorption lines. And the instrumentation has been there. We just haven't conceived yet of this potential idea to measure the relative abundance of helium-3 to helium-4 in gas clouds. And that's what I'm showing you here. So on the top left, you can see very strong absorption features that are due to helium-4 absorption. And on the top right, this blue arrow is pointing to a very weak feature, that is the corresponding helium-3 absorption that is shifted relative to the helium-4. In the same way that deuterium is shifted relative to hydrogen, helium-3 has one less neutron, it gets shifted to redder wavelengths. And I should mention this data is the black, and it's hiding behind the red, which is the model fit to the data. And the data have a resolution of like 100,000. So this is one of the highest spectral resolutions we have available. It's also a signal to noise of about 1,300. So this is about the most exquisite spectrum that's ever been obtained in astronomy. And in 30 minutes, we managed to detect the helium isotope ratio. So to try and understand what this might mean, this is in our galactic backyard, and as Max mentioned, the Milky Way is not such a great environment that you want to measure a primordial abundance. So we checked this with galactic chemical evolution models. We used a code called VICE. And this tells us that we didn't change any of the input physics, we didn't tweak anything, we just used it straight out of the box. And it turns out that 70% of the helium-3 that's in the Milky Way today, around the Orion Nebula, is primordial. 70% is still primordial. Just 30% comes from stars. And we plotted where our measurement ends up, and it comes out here. Now, given that we haven't tuned anything, haven't touched anything, this is kind of exciting agreement. But more exciting is the fact that there is now a technique where we can, in principle, measure the helium isotope ratio. We've also now detected in another 2 gas clouds in the Milky Way a different galactocentric radii, the helium-3 absorption line. So stay tuned, because this is going to get tripled in a moment.
So the measurement is the red dot with the error flags.
That's right. The 1 sigma is the height of the error bars. Yeah. Thank you. So I now want to talk about the prospects where we can actually do this in a primordial environment. And I'm going to call upon gamma ray bursts as a possible environment where we might be able to do this in the near term. And on the right, you see an example of a gamma ray burst, one gamma ray burst that's known that has these helium absorption lines. And so there's a real possibility with just the right setup, just the right timing, and we detect just the right system, that we could potentially be able to measure the helium isotope ratio in a near pristine environment. I think that's exciting for the future of Big Bang nucleosynthesis. Helium-3 has been traditionally extremely tough to measure. Okay, I wanted to end this, this lecture by talking to you about where I think the prospects are for the deuterium abundance, and what the future prospects are, and whether there's an exciting time ahead. And of course, the punchline is yes, there is. So to do that, I'm going to show you the quasar luminosity function. That's what's shown by this curve. Basically, it's just number of quasars on the y-axis as a function of how bright they are. The bright ones are on the left, the faint ones are on the right. And so there are many more faint quasars than bright quasars. So far, we've been targeting these quasars, highlighted by this blue region, with our current best telescope facilities and best instrumentation. With future telescope facilities, we can go down to these quasars. And that's extremely exciting, but I don't think you quite understand the message here. So let me show you in a different way. Here's 10 degrees by 10 degrees on the sky. And as you can see, there are about 8 quasars that we can currently detect with current facilities and observe to potentially get deuterium. Probably none of these will have deuterium because the statistics are so low. Now, with the future generation telescopes, we'll end up with, on the same patch of sky, this many quasars. And so that is transformative. We're now talking, because of the steep shape of quasar luminosity function, we're now seeing 100 times more quasars. That's 100 times more statistics than we currently have. That's reducing things by a factor of 10.
Is this because you have a bigger telescope or more sensitive detectors?
It's both. Yes, it's both. But it's primarily having a larger collecting area. It allows you to get to fainter quasars and beat above the beams. although that requires the lasers to be not quite so intense as shown here in the figure. It almost looks like it's melting the telescope. But I don't think it's going to be like that. I also want to talk about a new instrument that I'm excited by, and this is happening in the next sort of 5 years. I think this is going to be really groundbreaking in the next 10 years, where we'll have the measurements in hand. And so CUBES it's going to be attached to the VLT, which is an 8-meter class telescope, but it is UV sensitive all the way down to the atmospheric cutoff. And so the systems that Max and I have been working on for so long are at this sort of redshift range, around redshift of 3, where the lines appear in the optical range very comfortably. With CUBES, we could push this down to the near UV range at around 300 to 400 nanometers. Now, there's a lot of great potential here because at lower wavelength ranges, we can attack D to H absorbers at lower redshift. Compared to what we've previously been able to do, these absorption lines are cleaner. From Max's talk, we learned that there's a whole range of blending that we have to deal with in order to extract these measurements. So we go lower redshift, it gets cleaner. There's also more quasars at lower redshift. Those quasars are also brighter. And so, and CUBES is also more efficient than previous spectrographs, which were made 25, 30 years ago. And so, we're now talking about a sample increase very easily, I think, at a factor of greater than 10. And my prediction is that within the next decade, we should see something at the level of a 0.2% measure of the primordial deuterium abundance. This will, of course, require all of those fields in physics to also help beat down their errors, in particular, the nuclear physics rate uncertainties for several key reaction rate uncertainties. So I want to conclude just quickly by reminding you some of the figures that you've seen in this half of the talk. So Max and I hopefully talked to you about, and you've learned that Big Bang nucleosynthesis allows us to study the universe from its very first moments up to about a day after the Big Bang. We've also given evidence that the metal core damp Lyman alpha systems that we've been using for this measurement are perhaps the best environments to measure the primordial deuterium abundance. We've used these to infer the baryon density of the universe to a precision of about 1%, which is about 5% of the entire mass density of the universe today. Most striking is that there is an agreement between two completely independent probes in cosmology, and this stands as one of the pillars of our current cosmological understanding. I think there's a lot of potential for the future, so I'm really excited that we can attack all of the different nuclides in cosmology. We can measure helium-4 abundances, helium isotope ratios, and I hope we can also start working towards solving the cosmic lithium problem as well, and obtaining new measurements of that quantity. Finally, new instruments that we have in the future will allow us to search for and place strong limits on the departures from the standard model. And given the cracks that we're currently seeing, there's a good chance, I think, that we'll make fundamental progress in our understanding of the universe in the near future. Before I finish, I just wanted to say, again, Max and I would like to thank the Gruber Foundation again for your very generous support and for the committee for recognizing this work that Max and I have loved doing and really, really enjoyed. We also want to thank our collaborators, in particular Chuck Seidel, who was the 2010 Gruber Cosmology Prize recipient, as well as Michael Murphy, Regina Jorgensen, and David Bowen, who we have worked with over the years and have helped to contribute towards our understanding of the primordial deuterium abundance. And I will leave you with this thought and less lasers. Thank you.